Complex numbers. Let's start by reviewing the imaginary unit. In this section, when we see the letter I, that is going to equal the square root of -1. That's called the imaginary unit. And therefore, if I square both sides, I squared would be equal to -1. And this is going to happen when I take the square root of a negative number. I'm going to get out the imaginary unit. So I have the square root of -b is equal to the imaginary unit I times the square root of just +b. In this example, we want to write as the product of a real number and I, and then we're going to simplify. So the first thing we're going to do is recognize that this is the square root of a negative value, so that means that the imaginary unit comes out of it. So I have I times the square root of 80, and from here we're going to simplify the square root of 80. So we're looking for the biggest perfect square that divides 80. So in other words, this is I, and then I have 16 times 5. And the square root of 16 is 4, so we're going to express this as 4i and times the square root of 5. And we do typically put the coefficient 4 in front of the imaginary unit and then the radical part of the expression. And we'll go ahead and try that one more time for practice. So I have a negative underneath the square root, so that's going to come out as the imaginary unit times the square root of 48, and 48 is divisible by 16 as well. It's 16 times 3, and the square root of 16 is 4, so we have 4i times the square root of 3. So now let's talk about, well, when does the square root of a negative number come up? So in these examples, I'm asked to solve each equation over the set of complex numbers. So that means that the imaginary number can be a part of my answer when it says over the set of complex numbers. So here, if I have x squared equals -9, and I attempt to solve for x, what we would do is take the square root of both sides, but we would have plus or minus the square root of this negative number. So this is an instance where the square root of a negative arises, so in trying to solve certain types of quadratics. And so the negative is going to come out as the imaginary unit, so I have x equals plus or minus the square root of 9, and then I have times I'll just go ahead and leave it in the back for now, because the square root of 9, of course, is just 3. So what we have is x equals plus or minus 3i as my solutions. So if we were to have taken an algebra class, sometimes when we have a negative underneath the square root, we're told to write there's no real solution, and that's because we're solving in algebra typically over the set of real numbers. But because we can solve this over the set of complex numbers, we can leave I in our answer. So there's two answers here. There's -3i and +3i. And yes, you can write that as the condensed plus or minus 3i. Just wanted to make sure we know this is two separate answers. In this example here, very similar type of problem. We're solving for x in this quadratic equation, and so what we can do is go ahead and subtract the 24. So I have x squared equals -24. And just like last time, to solve for x, if we take the square root of both sides, we get plus or minus the square root of -24. So we're going to have that I come out of there. So I have plus or minus, put the I in front this time, the square root of 24. And 24 can be broken down into 4 times 6. So the square root of 4 is 2 here. So I'm going to have plus or minus 2i times the square root of 6. So I'm skipping a little bit of the steps here because we should be able to simplify square roots. So 24 is 4 times 6, and the square root of 4 is 2. So the 2 came out. We put the 2 in front of I, and we put the square root part in the back. So here, these would be my two answers. We'll write it condensed as plus or minus 2i the square root of 6. Let's go ahead and take a look at a few more examples involving the square root of a negative number. This time we're asked to simplify. So here I have the square root of negative 6 times the square root of negative 10. And what I have to do first is go ahead and remove the imaginary unit from both of these square roots. So in other words, I have I times the square root of 6 times another I and the square root of 10. So what I have is I squared, and now I have the square root of 60. So when these are positive numbers underneath the square root, the 6 and the 10, I can go ahead and multiply those two parts together. So I end up with that square root of 60. And then of course the I and the I multiply together to be I squared. But I couldn't do that at the start of the problem, so just a quick little warning here. So if I would have multiplied the parts underneath immediately, that would have given me, incorrectly, the square root of 60. And that's not going to be the same answer, as you'll see, as our final answer, because we lost the I squared part if we just multiply the two parts underneath. So that's not actually a property of radicals. The only way I can multiply the parts underneath is if they're both positive. So that's why the first thing I have to do is take out that imaginary unit. So I'm going to go ahead and erase this because it's incorrect. I can't do that first, because I squared, as we looked at earlier when introducing the imaginary unit, is simply negative 1. And then let's simplify the square root of 60 here. So 60 is 4 times 15, so this is negative 1 times the square root of 4 is 2. And then I would have the 15 left underneath the square root. So my final answer here is negative 2 the square root of 15. Let's go ahead and take a look at the next one. I have the square root of negative 40 divided by the square root of 2. So the first thing is to remove the imaginary unit, that square root of negative 1. So I have I, the square root of 40, divided by the square root of 2. And now, because I have both of these positives underneath the square root, I can divide the parts underneath. So I do have I and the square root of 20 remaining. And 20 is 4 times 5, so the square root of 4 is 2. We'll be able to take a 2 out. So I have 2i times the square root of 5. In our last example here, we have negative 8 plus the square root of negative 128 all over 4. So again, the first thing is I'm going to take out the imaginary unit as my I. So this equals negative 8 plus I times the square root of 128 all over 4. And from here we'll simplify. So 128 is 64 times 2. And 64 is 8 squared. So what's going to come out of here is an 8. So I'm going to end up with negative 8 plus 8i. I'll put the 8 first. 8i. And then the square root of 2 all over 4. And now there is some simplifying we can do. I can't cancel like this 8 and this 4 here. What I can do is I can split it up. So I can think about this as negative 8 divided by 4 plus 8i rad 2 divided by 4. So each term in the numerator gets divided by 4. And now each of these simplifies. So I have negative 2 plus 2i rad 2 as my simplified answer. Let's finally take a look at what a complex number is. We've been talking about the imaginary unit, but the imaginary unit is just a part of a complex number. So a number of the form x plus yi is called a complex number, where x is called the real part and yi is called the imaginary part. So if I have x plus yi, that whole thing is a complex number. And we break it down into the real part, the part without the imaginary unit, and the imaginary part, the part with the imaginary unit. Let's go ahead and perform some operations like addition and subtraction to begin with complex numbers. So in this example, we're just going to add and subtract the real and imaginary parts from one another. So I have -1 plus 3i, that's one complex number, minus 10 minus 4i, a second complex number. So here, what we can think about is this negative really is distributing to both parts of the second complex number. So I can think about this as -1 plus 3i minus 10 plus 4i, when that negative here distributes to the -4i, or that subtraction distributes. So now we just go ahead and add our real parts together. So -1 plus -10, or minus 10, so that's going to give me -11, and then plus 3i plus 4i, so that's plus 7i. So this here is subtracting two complex numbers. It's, again, just like adding or subtracting like terms from one another. And then here I have 2i and then minus 3 minus 4i. Notice the first complex number doesn't have a real part. The real part is 0, so it's like having 0 plus 2i, but we wouldn't write the 0. And then minus 3 minus 4i. So once again, I will think about this as distributing -3 plus 4i. And we do write the real part first, so I'm going to go ahead and write the -3. And then 2i plus 4i is plus 6i. The next operation we can perform with complex numbers is multiplying complex numbers. So we'll find each product and simplify it. So here I have 4i multiplied by 3 minus 5i. And we would go ahead and distribute in the 4i. So we'll go ahead and do that and end up with 12i minus 20i squared. And this is where we're going to remember that I in this section is considered the imaginary unit, so I squared is equal to -1. So I have 12i minus 20 times a -1. So the -20 times -1 will actually give us positive 20. So I have 12i plus 20. And I am going to go ahead and write that as 20 plus 12i. Again, we do typically write our complex numbers with the real part expressed first. Now here I have a complex number times a complex number again, but this time I'm going to have to use the technique of distributing in both terms. So a lot of students recognize this as foiling. So we're going to multiply the first terms, 4 times -2, so I have -8. The outer terms here, so 4 times 5i is plus 20i. The inner terms, -3i times -2 is going to give me a positive 6i. And the last terms are going to give me -15i squared. So now there's a few things to do. I can combine the middle terms together, so that's going to leave me with -8 plus 26i. And just like last time, I squared is -1, so I have -15 times a -1. So that's going to give me a positive 15 that I'm going to add to the -8, so that's going to leave me with a positive 7 plus 26i. So it's helpful to just remember here that I squared is -1, so essentially this is a positive 15 that we have, and we're subtracting 8 from it. And finally, this last one, we're multiplying again. We have 2 plus 2i as a quantity squared. And I just want to remind us one last time, or one more time, that the exponent does not distribute over addition or subtraction. So what we have to do here is remember that this is 2 plus 2i times 2 plus 2i. So just like the last problem, I have to distribute or FOIL it out. So we'll have 4 plus 4i plus 4i, and then plus 4i squared. Well, 4i squared is going to end up being a negative 4 because the I squared is a negative 1. So 4i squared and positive 4 over here actually cancel out. So these two pieces cancel out. So all I have left is 4i plus 4i, which is 8i. So I lost the real part of the complex number, but this would still be considered a complex number. And same thing if I didn't have an imaginary part, just a real part, that would still be considered a complex number. Now let's talk about dividing complex numbers. So to divide complex numbers, we need to multiply the numerator and denominator by the conjugate of the denominator. And our answer should be of the form x plus yi. So when dividing, we should still end up with a complex number. So let's remind ourselves of what a conjugate is. The conjugate of, let's say, x plus yi in general is x minus yi. So remember, we changed the sign in between the two parts, in this case the real part and the imaginary part. So we're going to multiply the numerator and denominator by the conjugate of the denominator. Okay, let's do it. Let's find each quotient. So I have 7 plus 4i divided by 2 minus 5i. So to divide complex numbers here, we're going to take the conjugate of the denominator. That's important. It has to be the denominator. So the conjugate of the denominator is 2 plus 5i. And we're going to multiply by that on the top and on the bottom. Oops, 2 plus 5i. So we can do that because this is like multiplying by 1. And what this amounts to is distributing across the top and across the bottom. So I have to FOIL on the top and on the bottom here. So it's like two multiplication problems in one. So here on the top I have first, that's going to give me 14. Outer is plus 35i. Inner is plus 8i. And last is plus 20i squared, all over. On the bottom, something nice will happen. When we multiply by conjugates, the middle terms will cancel. So we'll show that our first term is 4, outer is plus 10i, but inner is minus 10i. So we can see those middle terms will cancel. And then minus 25i squared. So in the denominator here, notice that the middle terms cancel, and I squared is a negative 1, so a negative 1 times a negative 25 is positive 25, and positive 25 times 4 is 29. So that should always happen here. The denominator should turn into just the real part of a complex number, so just 29 in this case. In the numerator here, let's see, the I squared is a negative 1, so this will be a negative 20 plus 14, so that's going to give me a negative 6, and 35i plus 8i is 43i, so plus 43i. Now we're not quite done yet. We do want to express our answer as a real part plus an imaginary part. So as ugly as it is, we're going to leave negative 6 over 29 plus 43 over 29i. So we split it up so that we could clearly have a real part and an imaginary part. On this example, I have 5 minus 4i divided by 2i. And so here, if we think about the denominator as a complex number, it's like 0 plus 2i. So its conjugate would be negative 2i. So it's like we could multiply by negative 2i in the numerator and in the denominator. But an easier thing to multiply on this example is just an I over an I. So I'm going to go ahead and kind of erase all this and really just multiply the numerator by I and the denominator by I. So here what's going to happen, this I is going to distribute, so I'm going to have 5i minus 4i squared over 2i squared. And then the denominator is just negative 2. So I have negative 2 on the denominator. In the numerator, the I squared is negative 1. So negative 1 and negative 4, that's positive 4. I'm going to write that first. 4 plus 5i. So notice the denominator is simply a real part. It's just negative 2, and that's what we needed to happen. Like over here it became 29. We needed the denominator to become just a real part, just negative 2, so that we can split this up. So this is 4 divided by negative 2, and then minus 5 over 2i, or negative 2 minus 5 over 2 times that imaginary unit. So here, why did we just multiply by I over I instead of negative 2i? Hopefully this kind of reminds you of simplifying radicals in the denominator, or rationalizing. So kind of just to throw in a review problem for a second, if I have 1 over rad 2, which we've been dealing with a lot in trigonometry, we would multiply the top and bottom by the square root of 2 to rationalize. Now if I had a, let's say, 3 on the bottom, I would still just multiply by the square root of 2 over the square root of 2. I can pretty much just ignore the 3, because the square root of 2 times the square root of 2 is just 2, and that gets rid of the square root. So here, just multiplying by an extra copy of I gives me that I squared, which gives me that negative 1, which gets rid of the I essentially. So that's why we don't have to multiply by the negative 2i, but it's different when there's a real part and an imaginary part in the denominator. Similar to if I had, 2 over 1 plus radical 2. If I was trying to rationalize this, I have to multiply by 1 minus rad 2, 1 minus rad 2, the conjugate of the denominator. So it's the same process. So this was dividing complex numbers. Powers of I. Express the powers of I in terms of I squared. Apply the fact that I squared equals negative 1 and simplify. So we're going to need these important facts over here. The first two we have been working with already. Here we're going to remember that when we take negative 1 to an even power, we end up with just positive 1. But when we take negative 1 to an odd power, we're going to get out a negative 1. So we're going to simplify each power of I here. So we're going to start by saying I to the 12th power is equal to I squared to the 6th power. I squared to the 6th power. So we're expressing the power in terms of I squared, and then we're going to apply the fact that I squared is equivalent to negative 1. So I have negative 1 to the 6th power. Well, a negative to an even power gives me a positive. So this is just positive 1. Let's try it again. So I have I to the 50th power. So once again, we want to express this in terms of I squared. Well, this is I squared to the 25th power. So our properties of exponents say we'd multiply these together. That would get us back to I to the 50. But this will help us because I squared is negative 1. So we have negative 1 to the 25th power. Or a negative 1 to an odd power, 25 is odd, so this will stay a negative 1. So this was working with I to an even power. So 12 and 50 were even powers. So the I squared to the 6th or I squared to the 25th, they worked out kind of nicely. These two examples on the right have odd powers. So let's see what to do with this. So I to the 121. So what we can do is we can express this as I to the 120 and then times an extra copy of I. So that's, of course, I to the first. So again, it's properties of exponents here. The 120 and the 1 would add together, so these are equivalent. And now we're going to work with this I to the 120 part, because we can make that, just like the last examples, as I squared, in this case to the 60, because 120 is 2 times 60. But we also have this I hanging out in the back, this I to the first power. That's the only difference. So now here, I squared, that's negative 1 to the 60th power times I, and negative 1 to the 60th power is going to be positive because that's an even power. So my final answer here is just an I. And we're going to go ahead and do that one last time for I to the 39th. So when it's an odd power, we're going to write it as I to the 38th times I to the first. So now we can work with I to the 38 since 38 is even. I can rewrite this as I squared to the 19th because 2 times 19 gives me 38, and we'll bring down that extra I. And then we have negative 1 to the 19th times I, and a negative 1 to an odd power stays negative. So I have a negative 1 times I as my final answer. So when we say simplify each power of I, there are only 4 possibilities. 1, negative 1, I, and negative I. That's what each of these is going to simplify to. That's the only possibility.